Okay, we continue our discussion on operational amplifier. So operational amplifier or op-amp is an integrated circuit amplifier with two inputs. The input at the positive is the non-inverting, input at the negative is the inverting, and then you have your output voltage. So in this example, D-in-1 will be the non-inverting input, D-in-2 is the inverting, and we have the output voltage. So for our transfer equation, the output voltage will be equal to the open loop gain. This is the internal voltage gain of op-amp multiplied by the difference between the non-inverting input and the inverting input. And in terms of behavioral circuit, this is the characteristics of op-amp. So within the input, you have the very high input resistance. So at the non-inverting, we have input voltage V1. At the negative input, you have the inverting input V2. And across the output, we have a voltage-controlled voltage source. So we'll have an output voltage equivalent to A sub O. So this is the open loop gain, the internal voltage gain of op-amp. AO multiplied by the difference between the two. Then for ideal characteristics, again, the input resistance of op-amp will be considered to be infinite. So we can always assume that the input terminals are open circuit. So that would be reflected later on with our circuit analysis. We can always assume that the input current into the op-amp will be equal to 0. Then, normally for practical voltage source, you have a voltage source in series with the internal resistance. For ideal characteristics, the series output resistance will be considered to be 0. So all of the output of voltage source will appear across the output. Then in terms of the internal voltage gain, again, A sub O is our AOL or the open loop gain. And for ideal characteristics, that is considered infinite. Then for the op-amp, the main advantage of op-amp having two input is the differential input. By having a differential input, we have the inherent noise rejection capability. So for every input terminal, along with the actual input, there would be a possibility of a random signal, or we call it unwanted voltage or unwanted current and so on. So whenever you have an unwanted voltage appearing on one of the input, the assumption is almost the same amount will also appear on the other input. So in any of the op-amp integrated circuit packaging, the two inputs are always placed very near with one another so that the noise produced in one pin would be the same on the other pin. So we can express our equation as the output voltage equal to open loop gain multiplied by this time V-in-1 has a noise. Together with V-in-2, it also have the same amount of noise. So because of the differential input, this random signal or the noise will automatically be rejected or canceled in our amplifier. So that would be main advantage of using our op-amp. Alright, can you follow so far? Ayan. Wave kung naintindihan. Ayan. Alright, so you have the automatic cancellation of noise. In terms of characteristics, we refer to that characteristics as CMRR. The characteristic or the parameter is denoted as the common mode rejection ratio. So common signal, you have it refers to your noise. And the amount of rejection is defined by the common mode rejection ratio parameter. Right? So we have here the differential input of op-amp has the capability to reject noise signals. Now, as for our inputs, again, we have the non-inverting input, that is the positive sign input. And with respect to the output, they have the same phase. If the input at the positive is negative, the output will also be negative. While if the input is positive, the output will also be positive. So they have the same polarity or same phase. So in this example, since the negative is connected to ground, so we can have a transfer equation of V out equal to open loop gain, since we don't have any feedback. So open loop gain multiplied by V in 1 minus 0. So V out will be directly related or proportional with the input voltage. While for the inverting input, we place the input voltage V2 at the negative with the positive input connected directly to the ground. And based on this transfer graph, we can see that when the input voltage V2 is negative, the output is positive. While when it is positive, the output becomes negative. So you have a 180 degrees out of phase or phase reversal. So based on this example, V out would be open loop gain with positive equal to 0, and then you have the input voltage. So the output will always be the negative of the input 2, right? Susundan pa? Okay, so this is more of a review. Nadaanan na rin natin to last time. Now, in terms of power supply and its effect on the output, so first we have here the LM741. That is one of the most common or popular part number for an op-amp. So it is a general purpose op-amp. So you have the LM741. And the common packaging is 8 pins. So this is the pin assignment of, let's say, a dual inline package. With pin number 1 assigned as the offset null, pin number 2, that is the inverting input. Again, we can remember the negative input by the figure of number 2. No? Pwede mo siyang i-visualize na parang letter L, indicating negative input. Then near that negative input, we have the positive or the non-inverting. Then at pin 4, you have negative supply. Then counterclockwise, the next pin would be pin number 5. So that would be the offset null. And then for pin number 6, that would be output. The recall would be the somehow small letter O on number 6. So that would be your output letter O, our recall. Then at pin 7, you have D+, and then pin 8 has no connection. Now, this is one way of presenting a dual supply circuit. So you have the 2 input, the single output, then you have the 2 power supply. If for LM741, it is a bipolar circuit. It means internally, it is using NPN and PNP transistors. So our notation would be plus VCC and negative VE. And if we are using a dual supply, so in this case, we connected VCC and VE, that means across the output, this is the expected output swing. The voltage across the output or the V out ideally can reach up to positive supply and down to the negative supply V. Right? On the other hand, when you have a single supply, again, how to do the single supply? All you have to do, the negative supply pin, connect it directly to ground. And when we do this, the output voltage will now only range from 0 going to the positive. Okay, so limited tayo pa. Okay, again, can you follow? Can you follow? Yes, all right. Hindi gumagano sa inyo. All right, this is our first circuit. We call it the voltage follower. We have discussed this last time, so I'll try to skip this over. All right, so for a voltage follower or unity gain follower, the main characteristics is the input voltage is connected at the non-inverting, and the negative input will be directly connected to the output. Right? So following this, V out is open loop times V in. The positive input is V in, then the negative input is also V out. Right? Then with a very high gain for the op-amp, we can assume that this is almost equal to 1. So you can have an approximation that V out is equal to the input voltage. And from last time, we also discussed the concept of slew rate. It describes the speed of the op-amp to change as the input changes. It describes the speed of the output voltage to change alongside with your input. So going back on the slew rates, the test circuit to define the slew rate is using the voltage follower. Then we have here the non-inverting amplifier. Take note of the configuration. For the non-inverting amplifier, the input voltage must be connected at the positive. And then from output going to the negative, we have the feedback resistor R1. And from that node going to ground, for the negative input going to the ground, we have another resistor component. So to analyze what will be the transfer equation, from the input, we'll have the current going into the op-amp. Then some of that current will go out and will return back to the input as the feedback current along R1, going back to the negative input. And that feedback current will become input current to the negative input of op-amp, and some will flow through R2. So we can form a current equation on this node. Current entering is equal to the total of current leaving. So current along R1 equals current through R2 plus the input current to the op-amp. And applying these characteristics, the input resistance of op-amp is infinite. It means that the input circuit or the input terminal is equivalent to open circuit. That means the amount of current here can be assumed to be 0. So we can set I equal to 0. Then for the current along R1, we apply Ohm's law. Current is voltage divided by the resistance. So for the current along R1, node voltage here minus node voltage at this point divided by resistance R1. So voltage here is V out. Voltage at this point is defined in this schematic as our V in 2. So you have V out minus V in 2 divided by R1. Equal to, for the current along R2, voltage drop across R2 divided by resistance 2. So you have plus V in 2 minus 0 divided by R2. So we have V in 2 over R2. All right, then we apply these characteristics. So for any op-amp, you have V out equal to open loop gain times voltage at the positive minus voltage at the negative, with an ideal voltage gain of infinity. That would make V in 2 or V in 1 equal to V in 2. All right, in order for AOL to be infinite, the input voltage must be equal to 0. So that means these two voltages are equal. It means in your schematic diagram, the voltage or potential on the non-inverting the voltage at the positive will appear also on the negative. So if you have here V in 1, then it means the voltage at V in 2 is actually also V in 1. Okay, so pwede nating i-substitute yun, no? So that would give us this transfer equation. Okay, so apply your algebra, then V out will be equal to, it would be R1 over R1 plus R1 over R2 times V. So for the non-inverting amplifier, this is our form. You have feedback resistance, resistor connected between output and negative input, divided by the input resistance. Resistor connected between negative input and ground. Then do not forget, meron tayo plus 1. Okay, so multiply it. Then another basic circuit, you have the inverting amplifier. Look at the schematic diagram. The input voltage this time will be connected at the negative, while the non-inverting will be connected to ground. So to analyze, from the input voltage, we have the input current passing through R2. Then at node X, that will be divided into current along R1 and current going into the op-amp. So again, applying current equation, current along R2 equals current along R1 plus the input current. And with open circuit at the input, we can assume that I in is equal to 0. Then apply Ohm's law to get the expression for the current. So current along R2, voltage drop divided by R2. So you have plus V in minus voltage at node X. And from the schematic diagram, the potential at node X equals, tingin ka sa kabila, no? Sabi natin, the potential on the two inputs are always forced to be almost the same. So the positive is directly connected to ground with 0 volt. Therefore, the voltage at the negative will be virtually grounded. It will have the same voltage equal to 0 volt. All right? So anyway, at this point, just using the variable x, you can write it as V in minus Vx over R2 equal to, for the current along R1, that is Vx minus V out over R1. And with infinite gain, it means that the voltage at the positive equals voltage at the negative. And therefore, with voltage at the positive equal to 0, the voltage at this node will also be 0. Or that is what we call the virtual ground node. Na-check nyo ba kanina sa lab? Yung kung totoo yung plus and minus? Almost the same. All right. Or you can do it also in LT Spice to double check whether really you have the same potential on the positive input and on the negative. All right. So applying Vx equal to 0, then we have this equation. V in over R2 equals negative V out over R1. And so the transfer equation equals negative of the ratio of feedback resistor, resistor connecting V out and negative input, divided by the input resistor R2, right? Multiplied by the input voltage. All right, so that would provide you a convenient way of producing an amplifier. So if you want to amplify a certain signal by 10 times, all you have to do is connect the circuit in your breadboard or in your PCB and use a component with a ratio in terms of R1 and R2, use a ratio equal to 10. So right away, you have an amplifier with a multiplication of 10. Any questions so far? Any questions so far? We have a participant. Hindi ko nakita. Halimbawa, Go ahead. Kung paano mo rin.
Try nyo daw, sir, mag-ano. Balik doon kay sir sa view options, sir, sa task ng screen.
Unmute mo, sir. Unmute mo, sir. Pila natin record.
Sige.
Sasabihin mo, sir.
Sir,
Yes, go ahead.
good afternoon, sir. Yeah, how are you there in the Philippines?
May request screen
It's really
annotation.
okay, for the annotation,
Okay, thank you, sir.
thank you, Sir Arnold. So for the annotation, for this example, from the input,
View options tayo. Tapos, annotate. Select na lang yung sir option.
pakita natin yan.
Select mo na.
Alright, so for this integrator circuit, take note of the schematic diagram. Input element is a resistor, then the feedback element is a capacitor. So to analyze, from the input, we'll have current passing through R1. So you have your current along R1. Then on this node, the current will be divided into input current. Then you have here a current along capacitor. Then all you have to do, again, formulate your equation on this node. Okay?
Tapos, sir, gusto nyo sir, try nyo rin remote desktop para dyan na rin kayo set sa ating view options. Request remote. Request. Para labukan ko sa user yun. I-allow nyo dito. Comment sa preferences. I-allow nyo.
Click ko ba ito? Nakikita niyo yung password?
Wala.
Okay, so
Check nyo.
okay na.
Then try again. Hi sir, you can control na lang. Bali, i-PowerPoint nila po sa computer.
Okay. Sa Zoom.
Full scan. Tapos dahil nyo po mag-click yun. Dapat pag-direct na. Can control. Then tap. Tap nila. Then dito.
Okay, mas maganda yun.
Para po, sige.
Right, so again, from the input, you have the input current, then okay, so you have the current along R1 equal to current along capacitor 1, then equal to Rin. Okay? So R1 equals IC1 plus IE. Again, input resistance of op-amp is infinity, so we can set input current to be 0. And therefore, you have IR1 equal to current along capacitor 1. Then recall that for capacitor, this is the characteristics. Current along capacitor equals capacitance times the change in voltage. So recall the basic functions of passive devices. Resistor opposes current. Capacitor opposes change in voltage. Alright, so whenever you have capacitor in your circuit, the voltage will not suddenly increase or will not suddenly or instantaneously decrease. It will introduce a certain time delay. It will take time to charge or to accumulate voltage. And the third basic passive device, you have the inductor. Basic function of inductor is to oppose change in current. All right, so again, resistor opposes current, capacitor opposes change in voltage, that is delta V over delta dt. All right, then inductor opposes change in current. Yun lang pag medyo malapit.
Yes.
Halos hindi ko na...
Mag-reactive.
Pag ba?
Dapat sir, parang PC ang sir, meron sa baba, yung araw sa power. Tapos malapit sa pangalan, dapat meron. Pag wala sir, keyboard lang. Pag araw ipak na lang.
Or maganda kung may paper.
Yes.
All right, so following this, current through resistor 1 plus V in minus voltage at node X is 0, right? So you have V in minus Vx over R1. Then current along capacitor following this, you have capacitor C1. Then multiplied by voltage across the capacitor, Vx minus V out. So delta Vx, quantity Vx minus V out divided by dt. And with AOL equal to infinity, again, the voltage at the non-inverting equals the voltage at the inverting. And since one of the input is grounded, the other node will be virtually grounded. So applying the 0 on the Vx, we get this equation. So V in over R1 equals capacitance C1 times the change in output voltage over change in time. So normally, using this equation, may mas-solve ka na dyan, no? You can approximate the result at the output. Okay, given the change in the, you can determine the possible change in the output voltage given the input voltage. Or if you like to further express it in terms of V out, you can integrate both sides. Alright, para matanggal yung derivative natin. No? So integrating both sides, then you can get V out equal to, lipat na to sa kabila, no? 1 over negative R1 C1 times the integral of V in times change in time, or with respect to D. Okay, so this expression proves that this structure provides integration, or ang tawag sa kanya, integrator circuit. Okay? So do not forget this. In some board exam, you have a easy question just asking what is the feedback element of integrating amplifier, and the answer is simply capacitor. Then for the differentiator, notice the adjustment in the schematic diagram. All we have to do is interchange the position of capacitor and inductor. Then from the input, you have current passing through capacitor. And then at node X, again, it will be input to the op-amp and current along R1. Then applying current equation on the node, you have IC1 equal to current along R1 and I in. And again, we set I in to 0. So you'll have IC1, current along capacitor, equals current along R1. Okay? Then use this equation. So IC1 would be capacitance C1 times change in voltage across the capacitor. So in this example, it will be plus V in minus voltage at node X is 0. So you can have derivative or change in input voltage. All right, so using this, you have C1 times change in V in minus Vx divided by dt, change in time, or delta t, equal to IR1 Vx minus V out over R1. And with very high gain, voltage at the positive is the same as negative. And so voltage at node X equals 0 volts. Applying that, you get C1 equal to change in input voltage over change in time equal to negative V out over R1. And from there, V out would be negative of the product of R1 and C1. By the way, the product of resistance and capacitance is also referred as the time constant. It describes the delay on the circuit. All right, so product of resistance and capacitance would give you the delay, the change in voltage for around 63%. All right, then it will take 5 times of R1 and C1 for the capacitor to be fully charged or fully discharged. So may ganun tayo characteristics. Okay? So you have negative of the time constant, product of R1 and C1, multiplied by delta V over. So again, based on this equation, we can say that this circuit, it acts like a differentiating amplifier, or it is a differentiator. Again, can you follow? Ganda pala itong pag-exam. Mako-control ba ito remote?
At the moment,
Ang teacher nasa bahay, si Gandhi na. Aganda kung ano.
parang kaya kasi nila. Sir, kailangan may nakita na application. May software yan.
Okay.
Pwede naman. Basic setup lang po natin.
Right. Ito nga pala tayo. Okay. Another circuit, we have the voltage adder. So instead of having just a single input resistor, we can connect a parallel resistor with another input. So this will give us an adding or summing amplifier. You can actually add more parallel components and you can add more signals. So it is not limited only to 2 inputs. Okay? So for this example, we have 2 input, V1 and V2, connected to the input of negative using R1 and R2. Then again, you have the feedback resistor RF. So for our analysis, V1 and V2 will provide current through R1 and R2. Then at node X, it will become input current to the op-amp and current along the feedback resistor. Then again, with very high input resistance, we always assume the input current of op-amp to be equal to 0. And we can always assume that the voltage at one input equals the voltage at the other input. So with one input grounded, this one will be virtually grounded. They will have the same potential. So based on that, our current equation will be current along R1 added with current along R2 equals current along the feedback resistor. Then use your Ohm's law. Current is voltage divided by resistance. So current along R1 would be plus V1 minus 0 divided by R1, or simply V1 over R1. Current along R2 is V2 minus 0, since that is virtually grounded, divided by R2, or simply V2 over R2. And for current along the feedback, 0 minus V out over Rn, or negative V out over Rn. Then, using your algebra, we now have the transfer equation. V out is equal to negative of the total or the sum of V1 and V2 multiplied by the respective gain. So for V1, our gain is Rf over R1. That is feedback resistance over the input resistance. Multiplier for V2, again, feedback resistance divided by the input resistance. So yun yung pattern natin. Alright? So to add, you can design the circuit in such a way that all components have the same resistances. So if R1 equals R2 and also equal to the feedback resistance RF, so the multiplier will be equal to 1, and therefore V out will be negative of the sum of V1 and V2. Okay, is that clear? Then we can also use this to get the average. If you want to get the average, we are adding two input signals. So if you want to get the average, add the 2, then divided by 2. Or we can right away multiply each input with 1/2. So overall, pag kinuha mo yung total nun, you get the average. So to get the average, we can set R1 equal to R2 equal to a certain resistance R, and the ratio of RF with respect to R will be equal to 1/n, where n will be the number of input. Right? So in this example, n should be equal to 2. So with that, you can have this equation. All right, V out is equal to negative of 1/2. So this will give us the average of the total of V1 and V2. All right, nasusundan ba? All right. And another application, we can also use the voltage adder as a mixer. So we can, instead of using a fixed value resistor, you can use a potentiometer for R2 as well as for R1, so that you can change R1 and R2. So for example, in V1, you can connect a microphone, and on the other input, you can have your accompaniment, let's say a guitar. Mukha gitara? Guitar yan, no? All right, so you have the human voice, and then the other one is the accompaniment. Okay, kapag pause yung vocalist, hihinaan niya yung gitara. Tama? So, you need to decrease the multiplier of V2, increase the multiplier for the microphone. So to do that, looking at this general equation, we want the gain of V1 to increase, while we want to reduce the gain for the V2. Ito yung guitar. And then this is the signal coming from the microphone. So to do that, what are you going to do with R1? To increase the multiplier, reduce R1, while for this one, we have to increase the value of R2. So you will adjust the potentiometer. Let's say you want to reduce R1. Based on this example, if you want to reduce, you may move the wiper towards the left, so that most of the resistor or most of the resistance will be shorted. So the effective resistance will only be this portion. So you're able to reduce that resistance. Now, in case you want to increase, you will move the wiper of your potentiometer to the left. All right, so the amount of shorted resistance will only be a small portion, and a large part will be functional. Effectively, you increase the resistance. Right? Is that clear? Is that clear? Okay, so clear. Ayan, clear na natin. All right, another one, if you have addition, we can also do subtraction. So take note of the schematic diagram. For subtracting amplifier, we are using both inputs. So far, if you notice, in previous examples, we are actually using only one input at a time. We are only using the negative input. Right? Or while the positive would be grounded. Or in the non-inverting, you are only using the positive input while the negative is connected to the ground. For the difference amplifier or for the subtractor, it is the circuit that uses both input of op-amp. We apply voltage at the negative input and another input voltage at the positive. Alright, so ganyan yung structure natin. So in this example, we have for V1, input resistance R3, then you have feedback resistor R5, connected between output node and the negative input. Then for the positive side, you have resistance R4 and R6. So to analyze from V1, you have current along R3, and that current will become a current passing through R5 and a current going into the op-amp. But again, because of very high input resistance, we will assume this current to be 0. So the equation on this node will simply be current along R3 equal to the current along R5. So IR3 will now be voltage drop across R3. So that would be V1 minus voltage on this node. So we temporarily label the voltage here as Vx. So we can say voltage drop across R3 as V1 minus Vx divided by R3. Then current along R5 would be Vx minus Vout divided by R3. All right, then that Vx will come from the other node. Right, so the Vx actually is the voltage across R6. So that voltage Vx is the voltage across R6. And if you look at this portion, since this is open circuit, effectively R4 and R5 are connected in series. So you can apply voltage division. So Vx in terms of voltage V2 equals resistance R6 divided by the total resistances of R4 and R6. Okay? So applying that on our equation, IR3 would now be V1 minus Vx over R3. Then IR5, Vx minus Vout over R5. And we can get the expression for Vout equal to, for Vx, multiplied by 1 plus R5 over R3. So if you look at this form, this is the same pattern for the non-inverting amplifier. If you look at the schematic diagram, Vx is connected to the positive. So Vx will be multiplied by the non-inverting gain. Again, the non-inverting gain is equivalent to 1 plus feedback resistance divided by the input resistance. Okay? And then minus feedback resistance over input resistance times V1. So this gives us the pattern for the inverting amplifier. So with V1 connected at the negative, it will behave like inverting amplifier. Nakuha ba? Okay, so be aware of those patterns. So when you do your derivation, pag sinusulat mo equation, you will readily know kung may namali ka. Paliwanag, okay? Then we substitute Vx using this voltage division. So we get Vout equal to 1 plus R5 over R3, feedback over input resistance, multiplied by voltage division, R6 over R4 plus R6 times V2, and then minus R5 over R3 times V2. Nasundan. Okay? So this will give us the general equation describing our voltage subtraction. Now, what will happen if R3 is equal to R5 and R4 is equal to R6? So that will give us a multiplier of 2 times, this will become 0.5, this will become 1, and so the Vout will be simply V2 minus V1. So you can have the direct subtraction of your two input voltage or voltages. Right? So can you follow? Thank you. Camera 2. All right, what about get to yung exam? All right, so ang approach, whenever you have cascaded or multiple op amps in one circuit, all you have to do is analyze it one at a time. All right, since each of the op amp is open circuit, has an open circuit input, it doesn't matter on the input or previous stages. All right, so the voltage here will not affect, or rather, the succeeding stages will not appear as load to the previous amplifier, since this is equivalent to the open circuit. So the approach is to analyze the op-amp circuit individually. Clear? So for example, by the way, this is what we call the instrumentation amplifier. Take a look at the schematic. What basic op-amp circuit can be found in instrumentation amp? Can you find inverting amplifier, non-inverting amplifier, summing amp, subtractor, or difference amp? Anong meron? You actually have subtractor. Document natin. No? Okay, what is the basic circuit in the instrumentation amp? A3 is subtractor. How about A1? Non-inverting. Or actually, it is also a subtractor. A2, again, when we say subtractor, you have two inputs. You have an input on the positive, and on the negative, effectively, we also have another input. The negative is not connected to ground. So it can perform as a subtractor or difference amplifier. Nasusunod, sir. Yung camera.
Pwede rin. Yung arrow keys. Long press lang para accelerate.
Okay, let us show other classmates.
Press na lang po pang siya 360 sir. Iikot po, iikot. Ano ba ito?
Ayos wala.
Ano, i-adjust lang po namin yung kanina sir.
Alright, so I'll return it on this side.
Yun na yung hindi siya 360. Iikot talaga.
360 siya, kaso one.
Send yun na lang. Yung 1, 2, 3.
Okay. Naka-program. Alright, sa inyo muna. Ito nakikita rin naman, sir.
Yes, sir.
Okay. So again, for the instrumentation amp, we actually have 3 subtracting amplifier. Again, the advantage of having a subtracting input is the common mode rejection ratio or the noise rejection capability. So amplifier 1 will be able to cancel any noise from V-in1 and from any noise on this input. And another one, amplifier 2 will also provide the noise rejection. And after having a noise rejection, you have the second degree rejection. Since you have another stage of amplifier 3, if ever there are still some noise, they will still be removed using the second level amplifier. All right, so therefore we can use instrumentation amplifier for very, very small signal applications, such as in biomedical electronics. As we mentioned before, if you use biosensor, normally from that sensor, you can only acquire microvolts or sometimes even nanovolts. So to remove any unwanted signal, you can use the instrumentation amplifier. Can you imagine kung nag-design kayo ng ECG, tapos sa GUI mo pumipitik pa, no? Yung pala noise na lang yun. Diba? So delikado yung mga ganung signal, no? So it must be very accurate in a sense na walang effect yung noise sa kapit. Or not accurate, it must be immune or robust in terms of noise rejection. Okay? All right, so again, if you are given with multiple op-amp, the approach is to attack it, solve it one at a time. So we start with amplifier 1. So first, we indicated the voltages. So this is V-in1. You have here V-in2. Then between amplifier 1 and amplifier 2, we have here a common resistor RG. This is actually your gain resistor. Okay, later on we will find out why it is labeled as the gain resistor. Then we have the overall output Vout. Then the principle of the same potential on the two input. So if the voltage here is V-in, the voltage at the negative of amplifier 1 will also be V-in1. Okay? The same with amplifier 2. If this is the actual V-in2, the potential on this node will be equivalent to V-in2 as well. Okay, clear? So we can now start analyzing amplifier 1. So what are the signals in amplifier 1? We have V-in1. And what is the voltage here? V-in1 also. What is the voltage on this node? V-in. V-in1, and then on this node you have V-in2. Then you have Vout1. We are going to label the output of amplifier 1 as Vout1. Then input voltage, current from V-in1 will enter the op-amp. Or again, in actual, there is no current. So it is actually the voltage entering or affecting the amplifier 1. Then some of that current will go back through feedback resistor R1. And on this node, it will become again input current and current passing or flowing through RG or gain resistor. Okay? Apply current equation on this node. You have current along R1 equals current along RG plus I in. So we know that I in is equal to 0 because of the very high input resistance. So using Ohm's law, current along R1 will be plus Vout1 minus V-in1 over R1. All right? And current along RG would be, so since the current is flowing down, so you have plus V-in1 minus V-in2 over RG. Okay, can you follow? Okay? Then,
Sir, naka-annotate na.
alright, then you now have V out 1 equal to this, so just distribute and we'll get this equation. So the output of amplifier 1 circuit, V out 1 is equal to this. You have 1 plus R1 over RGB in 1 minus R1 over RGB in 2. Again, the form V in 1 is connected at the positive. Again, it will be amplified similar with the non-inverting input. 1 plus feedback element divided by the input. While V in 2 is connected at the negative, so it will be multiplied based on the inverting amplifier gain. So minus feedback over input. Okay, nasundan ba? Then, so that's it. For the amplifier 2, for the amplifier 2, we have V in 2, and this voltage will be reflected on the other input. Then on this side, you have V in 1. Then we label the output here as V out 2. Right? So from the actual input, V in 2, you have the input current will go out, and some of that current will return passing through the feedback resistor R2. And then on this node, the feedback resistor will again be input to the op-amp and current along gain resistor R2. Then apply KCL on this node. You have current along R2 equal to current along RG plus IN. IN is 0. So IR2 means IR2. V out minus V in 2 divided by R2. Then current along RG, you have V in 2 minus V in 1 divided by R2. All right? Then again, process the equation. We'll get the expression for the output of amplifier 1. Again, look at the form. V in 2 is connected at the positive. So it will be multiplied by 1 plus feedback over the input. While V in 1 is at the negative, so it will be amplified using the inverting amplifier. So after knowing V out 1, V out 2, you can now analyze the next stage, which is amplifier 3. So again, for clarity, this is V out 1, this is V out 2, and then we have here the final output voltage V out. So similar with our analysis of difference or subtracting amplifier, we label the voltage on this node as a portion of V out 2. All right, voltage drop across R6, we label it as V out 2X. And that voltage will appear on this node. So meron ka ring V out 2X. Then from there, from V out 1, always form the equation on the feedback node. Okay, so in this example, the feedback is at the negative. Right? So current along R3 will become current along R5 and the current into the op-amp. So our equation will be IR3 equal to current along R5 plus IN. So IN is 0. Then for the current along R3, you have V out 1 minus V out 2X divided by R3. Then current along R5, it would be V out 2X minus V out over R5. Okay? So process the equation, we'll have V out in terms of V out 2X and V out 1. Okay? So again, tinan mo yung form, non-inverting and inverting. Then for the V out 2X, here is the voltage drop across R6. So apply voltage division. You have the V out 2 multiplied by R6 over the total of the series resistors. So, substitute. Ayaw na doon, no? Ito na. So, this is our equation. V out is 1 plus R5 over R3 times V out 2x minus R5 over R3 times V out 1. Then based on the equation for amplifier 1, V out 1 is equal to this. V out 1 is equal to 1 plus R1 over RG multiplied by the input of positive, which is V input, minus the voltage at the negative, R1 over RG multiplied by V. For amplifier 2, V out 2 equals 1 plus R2 over RG multiplied by the voltage at positive, so that will be V input, minus R2 feedback over input RG multiplied by the input of negative, so that would be V in 1. Right? So yun yung 4. Then from our voltage division, V out 2x is equal to this. So combine them together, this is our equation. Okay? So you now have V out in terms of the overall input, V in 1 and V in 2. So this is the general equation for this kind of instrumentation amplifier. Nasundan? So yung analysis naman simple lang. It seems lang na mahaba yung equation, but the analysis would be just stick to your basic in circuit analysis. And if you look at the equation, you have certain gain times V in 2 minus another gain multiplied by V in 1. So if you look in terms of amplifier 3, V in 2 is connected at the non-inverting. So that's why you have a positive gain. And V in 1, in terms of amplifier 3, is connected to the negative. So that is why you have a negative gain for the V in. So this is our equation, right? And what if all resistors are equal? R1 equal to R2 equal to R3, R4, R5, except for RG. Right? If all of the internal resistances R1 to R5 are equal to resistance R, so you have this expression. So if you simplify, this will give us the equation for the instrumentation amplifier. Okay? So you have V out equal to 1 plus 2R, where R is the internal resistance, right? Divided by RG, then multiplied by the difference of the two inputs, V in 1, V in 2, and V